Star notes. Stars in the nighttime sky are so abundant that they seem like they're almost next to each other, but in reality, they're really far apart. Stars are often seen in the nighttime sky as either individual points of light or as what we call constellations, which are groups of stars that appear to form a picture in the sky. When people, like the ancient Greeks, spent a lot of time outside at night, they would come up with myths or stories to explain the constellations. Now, constellations appear to move as night progresses because of the rotation of our planet. So it really is just our planet Earth spinning on its own axis. Compared to planet Earth and the other inner and outer planets, our sun is huge. But compared to other stars, our sun is really nothing special. If anything, it's on kind of the small end of the average star size scale. So if you're anything like me, you've probably wondered before, how does a star, like our sun, make so much heat and light every single day? Well, it's through a process called nuclear fusion, which is when you have hydrogen gases squeezed together with so much force and pressure that they actually will recombine to make the next more complex element called helium. And in that process, they give off a large amount of energy, equivalent to millions of atomic bombs going off every second, every day, for billions of years. So as our knowledge and understanding of stars increased, we started to need a way to compare stars to one another, and that's where the Hertzsprung and Russell diagram comes in. It compares three major characteristics about different stars. Mainly its brightness or luminosity, its temperature, and we do this by color, and star's size. So where does our sun fall in this HR diagram? Well, as you can see, our sun is in that main sequence category. It is yellow in color, and as far as temperature goes, it is kind of on the average or even cooler end of that spectrum, with red or orange stars being on the coolest end and the hottest stars being in kind of the blue and white category. All stars begin life the same way, in a stellar nebula, a giant collection of gas and dust, until nuclear fusion begins in the core and a star is born. Where it goes from there is totally dependent on the mass of the star at its birth. An average or low mass star, like our sun, begins as a nebula and moves into the main sequence, where it spends most of its time fusing hydrogen into helium to create energy. Then, towards the end of its life, when it's used up most of its hydrogen, it begins to fuse helium into heavier elements. This is known as the red giant phase, and it is kind of the last main stage of an average star's life cycle. After the red giant phase, the outer layers of the sun will expand out and be collected by another nebula somewhere else in the universe. All that's going to be left after the red giant phase is the exposed, extremely hot core of our sun, known as a white dwarf. And eventually, over time, since nuclear fusion is not going on anymore, that will slowly cool over millions and billions of years. It gets a lot more interesting for stars that are anywhere from 3 to 5 times or more massive compared to our sun, because they go through these stages of their life cycle a lot quicker. And you would think that the bigger the star, the longer it would live, but it's actually the opposite. The more massive a star, the quicker it fuses these different materials and the faster it goes through its fuel. So like the low mass stars, high mass stars begin life as a nebula. They move through their main sequence, fusing hydrogen into helium. But when that stage is finished and they begin fusing helium into heavier elements, then they will move into a supergiant phase because of their larger mass, and they will go supernova. And this is when iron begins to fuse and they create very, very quickly, giving off huge amounts of energy when they go supernova. They create all the other elements on the periodic table. And what's left at the very, very end is a very, very, very dense core, well beyond anything you'd get with the low-mass stars and their white dwarf exposed core. If a star is 3 or 4 times as massive as the sun, or a little bit less, then the exposed core is going to be what we call a neutron star. Now, a neutron star is nothing to laugh at. A spoonful of a neutron star would weigh as much, so one cereal spoonful would weigh as much as the entire mass of Mount Everest, the tallest mountain on Earth. And if you go beyond that, stars that are 5 times as massive as our sun or more, then the core that's left over is so dense, so compact, so infinitely compressed that it becomes a black hole. And a black hole can have a huge, huge amount of gravity in a very, very, very small space. So strong, in fact, that black holes can even absorb light. So there's really no way for us to see or take photographs of a black hole because there's nothing that reflects or is given off by a black hole. So if anybody ever asks you if our sun one day is going to turn into a giant, massive black hole, tell them it simply is not possible since our sun is considered a low-mass star.
Light is the fastest thing we know. It's so fast that we measure enormous distances by how long it takes for light to travel them. In 1 year, light travels about 6 trillion miles, a distance we call 1 light year. To give you an idea of just how far this is, the Moon, which took the Apollo astronauts 4 days to reach, is only 1 light second from Earth. Meanwhile, the nearest star beyond our own Sun is Proxima Centauri, 4.24 light years away. Our Milky Way is on the order of 100,000 light years across. The nearest galaxy to our own, Andromeda, is about 2.5 million light years away. Space is mind-blowingly vast. But wait, how do we know how far away stars and galaxies are? After all, when we look at the sky, we have a flat, two-dimensional view. If you point your finger to one star, you can't tell how far this star is. So how do astrophysicists figure that out? For objects that are very close by, we can use a concept called trigonometric parallax. The idea is pretty simple. Let's do an experiment. Stick out your thumb and close your left eye. Now, open your left eye and close your right eye. It will look like your thumb has moved, while more distant background objects have remained in place. The same concept applies when we look at the stars. But distant stars are much, much farther away than the length of your arm, and the Earth isn't very large, so even if you had different telescopes across the equator, you'd not see much of a shift in position. Instead, we look at the change in the star's apparent location over 6 months, the halfway point of the Earth's year-long orbit around the Sun. When we measure the relative positions of the stars in summer and then again in winter, it's like looking with your other eye. Nearby stars seem to have moved against the background of the more distant stars and galaxies. But this method only works for objects no more than a few thousand light years away. Beyond our own galaxy, the distances are so great that the parallax is too small to detect, with even our most sensitive instruments. So at this point, we have to rely on a different method, using indicators we call standard candles. Standard candles are objects whose intrinsic brightness or luminosity we know really well. For example, if you know how bright your light bulb is, and you ask your friend to hold the light bulb and walk away from you, you know that the amount of light you receive from your friend will decrease by the distance squared. So by comparing the amount of light you receive to the intrinsic brightness of the light bulb, you can then tell how far away your friend is. In astronomy, our light bulb turns out to be a special type of star called a Cepheid variable. These stars are internally unstable, like a constantly inflating and deflating balloon. And because the expansion and contraction causes their brightness to vary, we can calculate their luminosity by measuring the period of this cycle, with more luminous stars changing more slowly. By comparing the light we observe from these stars to the intrinsic brightness we've calculated this way, we can tell how far away they are. Unfortunately, this is still not the end of the story. We can only observe individual stars up to about 40 million light-years away, after which they become too blurry to resolve. But luckily, we have another type of standard candle, the famous Type 1a supernova. Supernovae, giant stellar explosions, are one of the ways that stars die. These explosions are so bright that they outshine the galaxies where they occur. So even when we can't see individual stars in a galaxy, we can still see supernovae when they happen. And Type 1a supernovae turn out to be usable as standard candles, because intrinsically bright ones fade slower than fainter ones. Through our understanding of this relationship between brightness and decline rate, we can use these supernovae to probe distances up to several billions of light-years away. But why is it important to see such distant objects anyway? Well, remember how fast light travels. For example, the light emitted by the sun will take 8 minutes to reach us, which means that the light we see now is a picture of the sun 8 minutes ago. When you look at the Big Dipper, you're seeing what it looked like 80 years ago. And those smudgy galaxies? They're millions of light-years away. It has taken millions of years for that light to reach us. So the universe itself is in some sense an inbuilt time machine. The further we can look back, the younger the universe we are probing. Astrophysicists try to read the history of the universe and understand how and where we come from. The universe is constantly sending us information in the form of light. All that remains is for us to decode it.